In 1666, a British-born scientist called Isaac Newton discovered the law of gravity. He discovered that when an object is dropped from a certain distance above the earth, the object will always fall to the earth's surface. He also discovered that when you throw an object upward, it moves, upward in this form and then fall back to the earth's surface. He said this is the law of gravity. 1666. But later on in 1687, he went ahead and published his book where he explained this law of gravity. So ladies and gentlemen, boys and girls, that means that the reason why we know that object that is thrown upward will fall to the earth's surface is because of this British scientist called Isaac Newton. Come on, don't tell me you believe that, because that's just crap. That's bullshit. We've always known that object that is thrown upward will fall to the earth's surface. You know that when I drop this marker from this point now, the marker will fall right to the earth's surface. We don't just know the term for it. We don't just know if you should call it gravity or something else. We don't really know how it works per se, but we've always known that objects obey or respect gravity. Now, Newton gave us a law called the law of universal gravitation. So we call that Newton's law of universal gravitation. This right here is Newton's law of universal gravitation. This law says that the force of attraction between two objects is directly proportional to the product of their masses, and inversely, of course there's directly here, and inversely proportional to the square of their distance apart. Now let me explain this law to you so you understand. Let's explain this law. Now this is an object, this is another object. Let's call this A and let's call this B. All right, there is always a force of attraction between these two objects. Right now there's a force of attraction between A and B. Why? Because A and B have mass. Whatever have mass must have force between it, or there must be a force attracting them together. A has mass, B has mass, therefore there's a force attracting them together. However, this force attracting them together will vary depending on the mass. If the mass, for example, let's say the mass here is 10 kilogram, the mass here is 10 kilogram, and the force is, let's say, 50 Newton. If the mass is increased from 10 kilogram to 100 kilogram, and this one now to 100 kilogram, the force will also increase in proportional form. That means that the force of attraction between this guy and this guy depends on the mass. The more the mass is, the more the force. The less the mass is, the less the force. In a nutshell, if the force between these guys now, the force of attraction between both of these guys now, A and B, make A and B to move in this form towards each other because they have masses of 10, 10. If the mass is now 100, 100, they will not move like this towards each other. They will move like this towards each other. That means the force is more because the mass is more, right? If the mass is not 100, 100, let's say 500, 500, then they move with better or with greater force. There is more collision. There is more physical interaction between both of them because the mass is more in this third scenario, as opposed to the second scenario where it was 100, 100, and the first scenario where it was 10, 10. That means that the force of attraction between any two objects in the universe, it can be this marker and this marker, it can be the marker and myself. I have mass as well. How do you know I have mass? It's very simple. How do you even know this marker has mass? You ask yourself this simple question. Does this marker contain tiny things called atom? If the marker contains atoms, the marker has mass. I have atoms also. I'm a combination of different atoms, right? Therefore, I have mass. So because I have mass, the marker has mass, there is a force of attraction between myself and the marker. There is also a force of attraction between myself and the earth, and between the marker and the earth. That means that there are three forces in play in this case now. A force between myself and the earth, the marker and the earth, myself and the marker, right? So let's say this is me, right? And this is the marker, and this right here is the earth. All right? Now we just explained that this force depends on the masses. You agree with me that of these three scenarios, or these three cases rather, the earth has the greatest mass here. The earth has the greatest mass, followed by me. Then of course the marker has the least mass, right? So because the earth has the greatest mass, the force between myself and the earth will not be the same as the force between the earth and the marker, or the force between the marker and I. Is that also? So between the earth and the marker, the earth and myself, if the force is 100 Newton, for example, we can then argue that between the earth and the marker, the force cannot be more than 100. The force should be less. because the marker has less mass, right? Let's assume the force in this case now is 20 Newton. And let's assume between myself and the marker, the force is way less, which is 2 Newton. So here we have 100 Newton, here we have 20 Newton, and this part is 2 Newton. What will happen as a result? Because the force between the marker and I, or myself and the marker now, is the least in this case. Because the force is the least in this case, that means that if I hold the marker like this, the marker will not move towards me. I will not move towards the marker. The force of attraction between myself and the marker is too small compared to the force of attraction between the earth and myself, the earth and the marker. By so doing, if I am to, let's say, jump from a story building, which I will not do for any reason in the world, but if I'm to jump from a story building, in that case, now that means I'm in air, marker is in air, and the earth is on its own. The marker will not move towards me. We will both move towards the earth. Why? Because it's more like what you have in biology, survival of the fittest. So what happens in this case is that all objects will respect the greatest force. That's the reason why the earth keeps moving around the sun. It's the reason why the moon also is moving around the earth, because you always obey the greater force. All right, so I've explained to you now that the more the mass is, the more the force. The next explanation now is the distance. Let's say you have this as an object, right? Let's say this is A, and let's say this is B. Let's assume the sizes are the same, and the distance between them is 2 meters. All right. If for one or two reasons or any reason at all, I decide to increase the distance, this part is still A, but now we don't have B here. Let's say what we have here now is B, and the distance has increased. From A to B is 2 in this case. From A to B is 4 meters in this case. Assuming the masses are the same, do you think that the force between A and B will still remain the same? Considering what the law said, it said, and inversely proportional to the square of the distance apart. So will the force remain the same? Will the force increase or the force decrease? In this case now, because distance is more, the force will decrease. The more the distance, the less the force. The more the distance, the less the force. The smaller the distance, the more the force. That means I can have an object here. Let's say object of 10 kilogram, and that object of 10 kilogram. The force between this object of 10 kilogram and 10 kilogram will be more than the force between an object of 1000 kilogram and that object of 2000 kilogram that are found, let's say, 3 billion meters from where I'm standing, or let's say 300 meters or 300,000 meters or whatever from where I'm standing. So my point is, with regards to mass, forces increase. With regards to distance, the force will always what now? Decrease if the distance increase. That's the meaning of this, inverse proportionality sign. And now, if you check the law, what we have here is inversely proportional to the square of their distance apart. Now, let me explain that part. What it means is that if, for example, the force between these two guys is, let's say, 2 Newton. For example, the force is 2 Newton. Distance, for example, is, let's say, 2 meters also. If I increase the distance from 2 meters to 4 meters, what does that tell you? Distance have doubled, right? It was 2 meters before. Now distance is 4 meters. One might think that the force in this case will become 4, but that'll be wrong. I just explained to you that when distance increase, force will decrease, right? So you might be thinking that if distance changes from 2 meters to 4 meters, the force should change from 2 Newton to 1 Newton, right? It will not change from 2 Newton to 1 Newton. It will change from 2 Newton to 0.5 Newton. Meaning to change from 2 Newton to 1 Newton, then you take half of 1 Newton, which will now become 0.5 Newton. That's the meaning of the square you have here. Meaning they are proportional inversely, but to the square of the distance between them. Meaning the more the distance doubles, the more the force now will not just become half, but become a quarter of the former value. You understand? Now, gravity is so important that if I simple to explain gravity, or to understand it very, very well, is think of gravity as an elastic string. So another way to explain gravity, based on what I've said now, is think of it as, let's say you like to jump, you like to play, right? And then you have a mom that is a soldier, a retired soldier, Nigerian soldier. What do you think about the mom? The mom doesn't have to shout at you and tell you to stop jumping around. The mom will quietly tell you to calm down. That is gravity. Quietly controlling the movement of all objects that intend to leave the earth, or that is displaced or thrown, away or moved away from the surface of the earth. That is how gravity works. Now let's give the mathematical expression to show what we have said now about Newton's law of universal gravitation. All right, from the law, the force of attraction, so I'll come out and say F, between two objects is directly proportional to the product of their masses. So I'll use the symbol of proportionality, and then I'll say M1, M2. All right. The force of attraction between two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance apart. What is inversely proportional to the square of the distance apart? Force, right? So force is in two cases now. Force is directly proportional to mass. Force is inversely proportional to distance, right? So I'll come out and say F in this case is inverse to distance. Now I'm using square here because of the square they said here, right? Now these are mathematical expression of this English expression. The next thing to do is to convert this right now to a formula. How do we do that? F here, you pick one. F. Proportionality, you pick one. Proportionality. M1, M2, R squared. This is a numerator, this is a denominator. You combine and then you say M1, M2 over R squared. This is still not an equation. This is a combined expression of the first and second, expressions. Now, from this now, we can then get a formula. How? Change the proportionality sign to an equation sign and of course introduce a constant. When you do that, this becomes F equal to Km1 M2 over R squared. From experimentation, it was observed that K is equal to a constant which is 6.67 times 10 raised to power minus 11 meter square per kilogram square. This constant was now called Newton's universal gravitational constant. So if K now have a special name called Newton's universal gravitational constant, we can therefore say that F is equal to Gm1 M2 over R squared. Leave this upward now, we can therefore say that F is equal to Gm1 M2 over R squared. This right now is the mathematical expression from Newton's law of universal gravitation. So if I give you a question, or you are given a question in JAMB that involve masses, that involve distance, and G is given to you, you can solve with this formula and get your answer. You can always solve with this formula and get your answer. All right. Not all the time you solve with this formula. Not all the time you solve with this formula. There are times when they ask you simple questions that don't involve everything. For example, I can ask you, if force between two objects, let's say object A and B, is 2 Newton and the distance between them is 3 meters, what will be the force between A and B if distance between them is 6 meters? In this case, you cannot solve with this entire formula. Why is that so? I gave you two forces. Two forces are here, but this equation have just one force. Two distance here, but the equation have just one distance. I did not give you M's. I did not give you M1. I did not give you M2. I did not give you G. So in this case now, you can't solve with this formula. How then do you solve? You pick that other expression you had before now. Before now we said F is direct to M1, M2. We also said F is inverse to 1 over R squared, right? You are not going to work with this. Rather, you pick this one. Why is that so? Because this is the only equation that involves force and distance. I'm going to change this. This is actually an expression, not an equation. If I change the expression now to an equation, this becomes F equal to K over R squared. How did I get this? Of course, I must change this symbol to equation. I must place a constant here. Therefore, I can say K is equal to FR squared. From what I have now, there is F here, there is R here. I can come around and say F1R1 squared is equal to F2R2 squared, right? What is F1, the first force, which is 2? I'll write it out. What is R1, the distance, which is 3? I'll write it out, 3 squared. Equal to, what is F2? Unknown. So I'll just come here and say F2. What is R2? 6, right? I'll come here and say 6 squared. To solve this further, I'll make the F2 subject formula. When I do that, this becomes F2 equal to 2 times 9 over 6 squared is 36. I'll come here and say 36, right? Now, 9 into 9 is 1. 9 into this is 4. That becomes 2 over 4. Your answer becomes 0.5 Newton. So if you observe, you notice that The distance changed from 3 meters to 6 meters. Because I explained before now that whenever distance increases, the force will reduce. One would expect that because distance increased from 3 meters to 6 meters, the force will just change from 2 Newton to 1 Newton. But what did you observe? It changed from 2 Newton to a quarter of 2 Newton, which is 0.5 Newton. Remember, I made this explanation just now before we go to this part. I explained to you that the distance is increased. The distance is increased. The force now will not just decrease. The force will decrease and decrease again. That the distance become double. Force become a quarter of the former value. The first value is 2. Force now becomes 0.5, which I explained before and which I have shown using this expression, using this question. That means that in cases where you have just force and distance, the formula to solve become F1 arrow 1 square equal to F2 arrow 2 square. The next part now is gravitational field intensity. Gravitational field intensity. Now, what is gravitational field intensity? The word intensity means strength. So when you say gravitational field intensity, you are also talking about gravitational field strength, the strength of a field, the strength of the region where there is gravity. All right. Now think of it this way. Let's assume this is an object, right? And this is the region around the object where its force can be felt or experienced. Meaning, this is the object, it has mass, and of course, this is the field, right? In case you do not know, in case I did not mention this earlier, any object that have mass must have gravitational force around it, right? And this force is found in a region around it called a field. Because it has mass and the force is called gravitational force, the name of the field is gravitational field. That is why the name of the topic is called gravitational field. All right. Now, if I place an object here and I place an object here, let's call this A, let's call this B. I have a question for you, and please give me the right answer. If an object is B, object is found at this point B, object at this point A, between A and B, which is closer to this object? B, right? So who do you think will experience more force? Will it be A or will it be B? Who will experience the force more? Who will be subjected to more force? B, right? Because B is closer to this guy than A. Because A is far away, the force on A will be minimal, right? If there's another object here, for example, the force of that object will be way minimal, or there might not be any force at all because it's very, very far from this guy, right? That means that the closer you are to this guy now, the more the strength which this guy pulls you to itself. Is that not so? That is what we call gravitational field strength or gravitational field intensity. It is the force exerted on a unit mass. The symbol for gravitational field intensity is given as E. Based on that, can come out and say E now is equal to force per mass. Force per mass. The force exerted on a unit mass, not a unit charge. When you talk about charge, talking about electricity. When you talk about mass, talking about what now? Gravity. So E is F over M. The unit is Newton per kilogram. You don't have to ask why this is true, because I mean, if force is Newton, mass is kilogram, it becomes Newton kilogram. Of course, in indices, you know that when you're moving something that's at the denominator or moving a denominator to become a numerator, you write -1, right? So E equal to F over M. Recall that F is equal to GM1 M2 over R squared. If F is equal to GM1 M2 over R squared, that means in this case, we can substitute F and say GM1 M2 over R squared all over M, right? E therefore is equal to GM1 M2 over R squared. It was over M here. That becomes divided by M. We also know from mathematics that we can change this to say E is equal to GM1 M2 over R squared now. In place of M, we can say times 1 over M. When we do this, M can go into M. E therefore is equal to GM over R squared. That means that for gravitational field intensity or gravitational field strength, we actually have two formulas. It can be force per mass, it can be GM over R squared. The next thing we are going to discuss now is the relationship between gravity on Earth and gravity on the moon. The gravity on the moon is always 1/6 gravity on Earth. Do not forget this formula, it's very important. And by the way, We already established two formulas from what we did just now, which was gravitational field strength. So I'll add it to what I have here now and say E is equal to force per mass, or Gm over r squared, right? Now I just added a new one and said G of mu is G of earth over 6. So this is the first formula, this is the second formula, this is the first formula, second formula, the third and fourth formula, the fifth formula. All right. And also do not forget that the value of gravity is 10, or you can say 9.8 mx minus 2. Gravitational potential. Gravitational potential. It is defined as the work done in moving a unit mass from a point in infinity to a point in the Earth's gravitational field. That means that if this is the Earth, for example, all right, and this is an object, the work done in moving this guy from here to here is what we call gravitational potential. The Earth must have the potential to do work. That's the reason why I can move this guy from here to here, right? Now that potential is what we call gravitational potential. Symbolically, it is given as V. So right now I can come out and say V, from definition, what we just said is the work done in moving a unit mass. I'll come out and say work done over mass. The unit in this case now, work done is always in joule. Mass is in kilogram. That becomes joule per kilogram. Recall that work is F times X. From work, energy, and power. If you don't watch the video, please watch the video. We said work is given as F times X, where F is force and S is displacement. However, in this topic, we don't always refer or use S to represent distance or displacement. We like to use arrow. If we use arrow in this case now, this becomes F. We say from above, comma, W is equal to F times arrow. If W is F times arrow, we can therefore remove W here and substitute with F times arrow. If we do that, V therefore is equal to F times arrow over what now? M. Recall again that this F is equal to Gm1 M2 over R squared. You know we said this before. If F is Gm1 M2 over R squared, if W is F times S, which cannot be changed to F times arrow, I can put F times arrow or can replace this W with F times arrow. That means V is now F times arrow over M, and now we can remove this F now, and replace with Gm1 over R squared. When we do that, it becomes V equal to Gm1 M2 over R squared, which is F now, times arrow over M. This becomes V equal to Gm1 M2 over R squared times arrow over M become times 1 over M. Over M actually means divide by M, but we can change divide by M to times. That becomes times 1 over M. It's the real mathematics. In this case now, V is equal to R can cancel one R here, M can cancel one M here. You now have Gm over R. This right here is the second formula for gravitational potential. The first formula was given, which is V equal W over M. So I'll come out and say V now can be W over M, just like when you have two formulas here, or V can be Gm over R squared. So you have two formulas in the case of this guy, also have two formulas in this case now. In this case, F over M, in this case, W over M. In this case, Gm over R squared, while here you have Gm over R rho, not R squared, Gm over R rho. And for gravitational potential, it is always negative because you are doing work. You are doing work towards the Earth. The Earth is doing work, so it's negative. You do work when you move things away from the Earth's gravitational field, not when the Earth brings it to itself. All right. If I move this duster right now from this point to this point, I've done work. I just moved it away from myself. But if now I bring it towards me now, that's negative work done. So that's why it always have negative. But when you solve your answer, you solve your question rather, and you check the options, and the options don't have the negative sign, pick the option that is correct in magnitude or whose value is the same as what you have solved, and you are very correct. Because let me give you a simple clue, a simple way to always know this and this. In the alphabet series, A, B, C, D, E, F. After E, it is letter F, right? So just know that whenever you ask a question or you ask for the formula for gravitational field intensity, you should know that is E equal to the next letter after E in the alphabet series, which is F over M. If you are asked for gravitational potential, the same thing. The next letter after V in the alphabet series is what now? W. So it is given as V equal to W over M. Do not say V is F over M. That's wrong. Do not say E is W over M. That is wrong. Always know that V goes with W, E goes with F. Another way to also think about it. This is V, right? This is V, right? Imagine I give you two V's in the same plane, or two V's that are arranged the same way. That becomes a W, which is what you have up here. Imagine I give you the inverted V. That becomes something like this, right? That becomes M, is what you have here. So my point is, what you have here in two places with the same orientation is what you have here. What you have here in two places in the opposite orientation, or the inverse orientation, is what you have here. This guy opposite, that's what you have here in two places. All right. So because what we have here is very similar to what we have here, the difference is just square. That's GM over R square and GM over R. We can therefore draw a relationship between E and V. Now watch me do it. Now let's show the relationship between E and V. The relationship between E and V is easy because we know E is GM over R square and we know V is GM over R. So how do we draw the relationship? Now, V is GM over R, right? Good. E is GM over R square. This is V and this is E, right? Can I come around and say E is GM over R times 1 over R? Can I do this? Yes, I can, because GM times 1 is GM, R times R is R square. So if this is the same as this, and this now is the same as what I have here, which is this, I can therefore replace this with V and say E is equal to V times 1 over R. But this V has a visible one. That's what we do in mathematics. In mathematics, when you have a whole number, let's say you have this, let's say A times 1 over B. This is just A. But because this is 1 over B, we assume in mathematics that there is a visible one here. After all, A over 1 is the same thing as saying A. You understand? So in this case now, if you do the same thing, because this part is V and this part is 1 over R, we assume there's a visible one here. So we now have E equal to V over 1 times 1 over R. That means E now is V over R. Now, we can also do the same thing here, right? If I say A is equal to B over C, this is like saying A over 1 equal to B over C. It's the same thing. Because A over 1 is the same thing as saying A. So if this is the same as this, we can therefore change this now and say E over 1 is equal to V over R. So now when we cross multiply, V times 1 is V, E times R is ER, as the formula that shows the relationship between V and E. There is V here, there is E here. What shows the relationship between V and E? This formula will be with the help of R. So I'll come here and say V is equal to ER as on that formula. So far we have the first formula, second formula, third, fourth, fifth, sixth, seventh, eighth formula so far. But anyway, I will not really say 8. I might just say 6 formulas because these two formulas are actually the same. These guys are also the same. This is not equal to. All right, escape velocity. This is defined as the minimum velocity required by an object to escape the gravitational pull of an astronomical body. All right. Now, how do we get this escape velocity? How do we get the formula? To get the formula for escape velocity, you must first of all bring out the equations of motion that will make a peak. There is V equal to U plus or minus AT. There is V square equal to U square plus or minus 2AS. There is S equal to UT plus or minus half AT square. Now, we want to escape from the Earth's surface. Let's assume this is the Earth's surface and this is the boundary of the atmosphere. Our job is to move from this point all the way to this point. How do we escape? What affects or what can hamper the plan to escape from the Earth's surface? Now, first off, if I must escape, that means I must move from this point to this point, right? That means that what I have now, what I've drawn, is an object moving upward. And for object moving upward, there must be initial velocity and final velocity. What am I going to have here? Initial and final velocity. That's right, initial velocity. What about the initial or final velocity? So there must be initial velocity, there must be final velocity. So I'll check my equations. In which equation do I have u and v? I'll check. Oh, there is u here, there is v here. That's good. There is u here, there is v here. That's also nice. There is u here, there is no v. So there's a problem for me. I can't use this. What else do I need for me to escape from the Earth's surface? If there is no gravity on the Earth, and that's not possible because the Earth has mass, there's always gravity. But if there's no gravity on the Earth, I won't consider the gravity, right? I'll just pick any formula and I'll solve. But in this case now, there is gravity. Gravity is always saying, don't leave. Come back to the Earth's surface. You know what I explained before? That invisible string that always attach all objects to the Earth's surface. That force I always say, come back to the Earth and do not leave. So if gravity is always saying, come back to the Earth, that means that for me to escape from the Earth's surface, I must have enough force to neutralize the Earth's gravity in order to get to my destination. To neutralize the Earth's gravity, I need to know what the value of the gravity of the Earth is to know how much force I will need to leave the Earth so I can escape it. Meaning, I need a formula that has U, that has V, that has G. And also, it will do me good if I know the distance from here to here. Imagine you are going to toss or throw a stone upward, and you are told to throw the stone in such a way that it escapes the roof of your, it flies above the roof of your house. If you are blindfolded, you throw the pen upward or you throw the stone upward, you can't really tell how far you throw the stone to make such escape. But if your eyes are opened and you can, guess the distance between yourself and the roof, then you know how much you should throw. So you do not throw too much or too little. So that means I need to know the distance, which is x now. I need to know x, distance from here to here. So what I need is v, I need u, I need g, I need x, right? So which of this equation has these guys? Definitely not equation 1, and of course not equation 3. It's gotta be equation 2. If you observe, there is time here, I don't need time, I just need to escape. So I'm picking equation 2. So I'll come out and say, from v squared equal to u squared plus or minus 2as. Remember that when an object moves upward, initial velocity is maximum, final velocity is 0. If initial is maximum and final is 0, can come here and say, oh, final is 0, right? I'll come here and say 0 squared is equal to u squared. Because the object is leaving the Earth, moving away from the Earth's surface, that means gravity becomes negative, right? That's minus. So I'll say u squared minus 2. A is g. S in this case means distance. And we mentioned something before now. I told you that in this topic, we always use r to represent distance, not s, right? So I'll change this s now to r. When I do that, this becomes 0 squared u squared minus 2g r. This u has a visible plus. When I move it this way, it becomes minus u squared equal to minus 2g r, right? Minus u squared equal to minus 2g r. I can change this u now to v. Why? It was called u, initial velocity, because there were two velocities. One was final, one was initial. But when you have just one velocity, you don't have to see there is initial or final velocity. You can just assume there is one velocity. In that case, I'll come here and say v squared, of course this minus can cancel minus, is equal to 2g r. Therefore, v escape is root 2g r as the formula for escape velocity. So I'll come here and say v escape is root 2g r. This right here is one of the formulas for escape velocity. What about the other formulas? Now before we give the other equations for escape velocity, let me quickly remind you, or quickly state now, that this is E, which represents gravitational field strength, or gravitational field intensity, or just gravitational field. If you don't use the symbol E, you can also use the symbol G. G and E mean the same thing. Alright? So, if that is true, it means we can say G is also F over M, or G is GM over R squared, right? You can say that, right? Good. Now, from what you have done here, we just show that escape velocity is root 2g r. So we can say escape velocity is root 2. If g can be this guy, therefore we can say gm over r squared times r, right? Therefore ve is equal to root. Now this r has a visible 1, so r can cancel one r here, so now give you 2gm over r. So I'll come around and say, oh, apart from this equation, there is another one that says 2gm over r. So I have two equations now for escape velocity, or two formulas for escape velocity. The last formula is this. You know before now that potential energy is given as mgh, right? Can we change this to a formula in this topic? Can we say PE is equal to mgr? Yes, we can do that, right? If this is true, can we say escape velocity is root 2PE over m? Yes, we can. Because if PE is mgr, we can therefore say VE is equal to root 2 times, in place of PE, we can say mgr over m. So that when m cancel m, what you now have is 2gr, which is 2gr. Therefore, the last formula for escape velocity is given as 2PE over m. So these are the three formulas or three equations for escape velocity. Now I know you are thinking, oh my god, see many formulas. How am I going to sketch through? How do I learn everything? I understand. But the first thing you need to understand from what I've said so far is that there is gravitational force. And it's not always the force. It can just be force and distance. This should not be easy. This should not be hard for you. This g or e equal to f over m g over r squared is the same thing as what you have here. What you have here is the same as what you have here. The little difference you have is, oh, f over m, w over m. Everything here is the same except the square. I had to give you this one because in questions in JAMB many times, they like to ask questions that pertain to this. They also tell you, what's gravity of the earth if gravity of the moon is 1.67? Or what's gravity of the moon? The gravity of the earth is 9.8. And when you do the division, you get 1.67. I just have to give this to you. And of course, this is the relationship between gravitational potential and gravitational field intensity. Then of course you have escape velocity. It is not going to be easy to learn, but if you commit yourself and do your work or do the work and put in the work, you will definitely learn these things. Next part now is satellite velocity. Satellite velocity. What is satellite velocity? It is the velocity with which a satellite, be it natural or artificial, orbits the earth or orbit a celestial body. So it can be the earth, it can be another celestial body. That velocity with which it orbits the earth or move around the earth or other planets or other celestial structures is what we call satellite velocity. And know something, it is also called orbital velocity. All right, another name for satellite velocity is orbital velocity. Now, to get a formula for this, centripetal force must be equal to gravitational force. This is the expression to get it. Centripetal force, which of course is the inward force that pull objects together, or the inward force that tend to make objects remain in their continuous circular motion, must be equal to gravitational force. So if, for example, I have this as an object, let me explain this. If, for example, you have this as an object attached to that object that is moving in a circle, all right, moving in a circle, you know that there's an inward force that is pulling this object towards this guy. That force is called what? Centripetal force. In same vein, there is a force between this guy and this guy, which you said before. There's a force between this object A and the object B. That force between them that depend on their masses and depend on the distance between them, we have explained before. That's the force we call gravity or gravitational force, right? So whenever centripetal force and gravitational force are the same, you can then look for the velocity with which this guy now is moving around the other one, which is called satellite orbital velocity. How do you do that? Fc equal to Fg. This become mv square over r, formula for centripetal force, equal to gm1 m2 over r square. Right? Now, m can cancel out m. You now have v square over r equal to gm over r square. If m cancel m and there's r here, the r can also cancel each other, right? So now say v square now is gm over r. So we can say conclusively that v is equal to root gm over r as the formula for orbital or satellite velocity. So this new formula now, I'm going to add to the formulas I've already expressed before, the formulas I've written out before. But the space will not be enough, so I'll just have to wipe up this part and add this formula here. All right, observe the formula we just gave now. This formula looks very similar to this formula. Take a look. Look very similar. Here you have root gm over r. Here you have root 2 gm over r. That means that the difference between satellite velocity and escape velocity is just 2, the 2 you have here now. Right? So if that is true, that means I can get other formulas for satellite velocity. Now come around and say Vx is equal to, I can take this guy now, remove the 2 and say root gr. I can take this other guy, remove the 2 and say Vs is root pe over m. So now I have the 3 possible formulas for satellite or orbital velocity gotten from the formulas for escape velocity. Now because they are related, because they look very much alike, I can then talk about relationship between Vx and Ve. All right. What is Vs? Vs, from what you have done now, is root gm over r. What about Ve? Ve is root 2 gm over r. I can split this and say Ve is root 2 times root gm over r. If root gm over r is root gm over r, then I can put this Vs here because everything here is Vx. So this becomes Ve equal to Vx root 2. This right here is the relationship between escape velocity and satellite velocity. Now you might be confused. Why did I not put Vs here and put root 2 here? Is the same thing. I'm going to do that. Becomes Ve equal to root 2 Vx. Saying root 2 Vx can be confusing in the exam because you might have a value for this, maybe 4 for example. I might be tempted to just say root 2, might tempted to say root 2 times 4, which will not give you the answer. That'll be wrong because the 4 is not within this root, this square root. You get the point now? The 4 is this Vs, and it's not within the square root. So it's better you place the 4 before the root 2 so you solve properly. So you say Vs root 2 so you avoid confusion. Now the last part of this topic, if you've watched the video to this point, you've been very, very patient, and I must commend you. I understand the formulas are a lot and it's not really easy to learn everything, but if you've enjoyed to this point, you're a genius, and I pray and wish you pass your exam. This is the last part, and it is the weight of object in space. Mathematically, the weight of object in space is the weight it is on Earth over n squared, where n is equal to d total over d radius. All right, I don't bore you the derivation of this formula, so just know n is equal to d total over d radius. D radius is the radius of the Earth, which of course is 6.4 exponential 6 meter, while d total is the distance from the center of the Earth to wherever the object is located. Now, so that I mean, if you ask a question, you're like, let's say you ask a question, they're like, what is the weight of an object that is found at a position which is twice the radius of the Earth from the center of the Earth? Twice the radius of the Earth from the center of the Earth. You want to calculate the weight. First off, if this is the Earth, this is the radius of the Earth, right? If an object is found here, let's say the weight is 10 Newton. If the object is now found here, this now is at the distance which is equal to the radius of the Earth. This distance now is the same as from here to here. So if I call this arrow, which means radius of the Earth, I can say this is the radius of the Earth also, and say this object is found at a distance equal to the radius of the Earth from the surface of the Earth, or at a distance twice the radius of the Earth from the center of the Earth. If it is not found here, I will say it is found at a distance which is equal to twice the radius. Please take into what I'm saying now, is very important. It's found at a distance twice the radius of the Earth from the surface of the Earth. See, after the surface now, you have this guy in 2 places, right? So you see twice the radius of the Earth from the surface of the Earth, or 1, 2, 3 times the radius of the Earth from the center of the Earth. So an object here, if it weighs 10 Newton, when the object is here, it will weigh less than 10 Newton. When the object is here, it will weigh less than what it was here. Why? Because you are leaving the earth. Because you are leaving the earth, the effect of the earth's gravity on you is reducing. And we know that the effect of the earth's gravity is what gives weight. The weight of an object is the product of its mass and acceleration due to gravity. So the more you leave the earth, the farther you are from the earth's surface now, the less the force. Remember, the more the distance, the less the force. So in that case now, the weight at this point now will not be the same as the weight at this point. If I'm to guess or give you a value of the weight at this point, what will I tell you? If at this point it is 10 Newton and now it is found at this point, which is now like a double of the distance, what will this be? Distance has become double. Will this become half or become half of the half? That's right, half of the half, right? So it will not change from 10 to 20, no. It will not change from 10 to 5, but rather from 10 to 5, from 5 to 2.5. What about this case? The same thing, become half of the other half. You get the point now? So that means that to know the weight of an object found at a distance above the Earth's surface, you need to know the total distance. So if I know total distance, which is, let's say from here now to this point, which is 3r, I can write it here. And of course, radius of the Earth, which is from here to here, I can write, so it becomes from here to here, 3r, v total, over, from here to here is just r. I'll come here and say r. R cancel r. What I have left is what now? 3. 3 square will not be placed here. If I put 3 square here, I still will get my answer, assuming I know the weight it is on Earth. You might not understand what I'm saying, so let me explain this. Let me give an example to explain this. Before doing that, I'll just add this formula to what I have here already, right? I'll add it to this part, and I'll wipe this part off, and I'll give a question to explain. Okay, so here's the question. A rocket has a mass of 9,000 kilograms on the Earth's surface. Calculate the weight if it is found at a distance 3 times the radius of the Earth from the center of the Earth. How do I solve? Whenever you see a question like this, where they're telling you about weight at a distance that is now found, that's now different from the center of the Earth or surface of the Earth, just like to solve this question, you need this formula. To solve, you first of all need to know the weight it is on Earth. So I'll come back and say weight on Earth. Weight on Earth is equal to mg, right? And from what we know, that becomes 9,000. Gravity is always 10, to give us 90,000 Newton. I've done that now. What I've solved now is for the WE. The next part now is for the n square. So I'll come back and say n square is equal to, let's start with n first. Whatever I get for a, that becomes the square. So let's start with n. What is the total? Calculate the weight if it is found at a distance 3 times the radius of the Earth from the center of the Earth. So if, for example, let me just draw it and wipe it off. If, for example, this is the Earth, and from this point, if this is the Earth, for example, and from here to here is the radius of the Earth, this object now is found at a distance 3 times the radius of the Earth, meaning this distance now 3 times radius of the Earth from the center. So if it is found at a distance 3 times this guy, but from the center, that means I'll come here, do this, come here and do this. This is arrow, this is arrow. You might be thinking now that I should draw another one. No, I will not do that. They said 3 times 1, 2, 3. 3 times the radius of the Earth from the center. Meaning 3 times you are talking about now is where you come from the center. Oh, as I will say, from here to here now is 1, 2, 3. The way you interpret this, you will say 3 times the radius of the Earth from the center, or 2 times the radius of the Earth from the surface. If they have not said 3 times from the center, they will say 2 times from the surface. It means the same thing, right? So if this is 3 times, now this is total distance, and from here to here is not my total distance. So I'll come here and say 3 arrow over, what about this guy? D radius, that means radius of the Earth, right? Radius of the Earth is what now? Arrow. I'll come here and say arrow. All right, arrow cancel arrow. When that happens, I'll come out and say this is equal to 3. And because we know it is n squared, that becomes 3 squared, which gives us 9. Therefore, the weight in space become 90,000, which is the weight on Earth, which we've solved already, over 9. This become 10,000 Newton. So what does this tell you from what you have solved now? What this shows to us is that an object weighs more on the surface of the earth and weighs less above the earth's surface. In pidgin English form, what they try to talk be say, if I carry bag of cement, this is my bag of cement na 50 kg, and 50 kg normally na 500 meter. If I carry bag of cement from here now, I carry and go where all those kind of cloud dey, like up where plane dey, all those kind of place now. If I carry that bag of cement reach there, bag of cement wey be say me no go fit use to and take raise for earth for here. Normally I dey raise am o, no be reason am, just that I dey try explain something. If normally for earth now, say maybe you no go fit raise the bag of cement for earth now. If you come reach that place, that for space now where aeroplane dey, all those kind plane, helicopter and the rest of them, you go surprise say bag of cement you no fit raise for it before, you use one and take raise am, e go follow you. If I say make you still go far, make you go far place, omo you no even gats use full hand sef. If you use one hand take raise am like this, e go follow you. So my point in a nutshell is that the more the distance or the farther you are from the influence of the Earth's gravity, the less likely the force will play a role on you. The more easy it will be for you to lift objects because they'll become less weighty. That's my point. So from this topic, see all the formulas we've been able to draft out. I had to take the formulas in order and not wipe any of them so you can have a general view of the entire formula. So you can make a screenshot of this after watching the video. All right, and then the next video now will be where we apply some of these formulas to solve questions. I'm Dr. Olotu, and I'm here to help you fix JAMB before JAMB fix you.